Well, these people will have to get a written definition for these ones. So amphiprotic, amphoteric, yeah, again, it's something that can be an acid and a base. And like I said, there's some ways that you can talk about this. A pKa value is a way to define the strength of an acid. And Blumling, I think, talks about that a little bit later in the semester, so don't worry about all that. But H2O, water, we can think of it as being both an acid as or a base. So what would the conjugate acid of H2O be? Mhm, exactly. So we have this guy here. Let's write con.
That conjugate is exactly the opposite of what an acid would do. When a conjugate acid is adding a hydrogen, but an acid will lose.
Yes, so you got it. Um, the way I've set up this problem, you're right. We're kind of thinking of it backwards in a way. And so the conjugate base would then be OH minus. And again, what is the like fancy name for this ion? Hydronium. Yeah, and this one, hydroxide. Sorry about that. Yeah, so this is kind of tricky at first, but a good thing to remember is if we were going over here to form this conjugate acid, what would H2O have to be acting as to form a conjugate acid? Maybe it wasn't the best way of wording that. A base, yeah. So this is some tricky stuff, and this does take some time for people to have it click. But to end up forming this conjugate acid, water would have to act as a base. And that's a good way of kind of showing how this is amphiprotic. If this acted as a base, we can imagine it doing what bases do. Bases grab protons. So it could grab a proton and form the conjugate acid. Now, if we look over here, if we're forming the conjugate base, what does this guy have to act as? An acid. Yep. Acids do what? They donate protons. So if this guy was acting as an acid, it would lose one of its protons somewhere else and form its conjugate base. So again, these are all different vocab terms, but it's really important to have a good understanding of this now. We can go a little bit quicker through the next few because it's kind of the same idea. But H2PO4 minus is another one of these amphiprotic species. So what would its conjugate acid be? You nailed it. And also, again, since when we add a proton, protons carry a plus ion charge. So if it was initially H2PO4 minus, as we add one proton, we're adding a plus to kind of cancel that out. So this is now a neutral compound. Then over here, if it was acting as an acid and we formed its conjugate base, we're going to dump off one more proton. So it's going to become HPO4 2 minus. Cool. And then same idea with this last one, HCO3 minus. If we're adding a proton to form its conjugate acid, it'd become H2CO3. And this is now a neutral species. And if we were acting as an acid and forming its conjugate base, we would get CO3 2 minus. So the polyatomic ion stuff from 131 does kind of come back up again in the acids and bases units. Okay. Do we feel pretty good with that stuff? Cool. As you're seeing, there's a lot of conceptual stuff with this exam, so I don't know exactly how he's going to go about testing it, but make sure like you have a really good foundation of the concepts behind acids and bases. Yeah, I think he tries to do that for every exam, so there should be one. Um, cool. All right. Here's another example of acids and bases chemistry. So I'm asking which reaction has HCO3 minus acting as an acid and which one as a base. So HCO3 minus, again, is an amphiprotic species. And we have two different equilibrium reactions up here. I know it's equilibrium because we have a forward and reverse arrow going on. And one of them is kind of showing HCO3 acting as a HCO3 minus, acting as an acid, and the other one has it acting as a base. So let's start up here. Let's kind of walk through it. We have HCO3 minus going to form H plus and CO3 2 minus. So what did it do from here to here? It lost a proton. So what do we think HCO3 minus is acting as in this top one? Acid. Yep. And we go down here. HCO3 minus is combining with a proton to form H2CO3. So this is acting as a base. It's basically going and grabbing hold of a proton. Cool. Now let's get into the math stuff, because this is what we were doing all of yesterday on the active. We have an aqueous solution at 25 degrees Celsius, and I'm saying if the HCO3 plus concentration is 6.2 times 10 to the minus 4 molarity, then what would the hydroxide ion concentration be? And then as a little bonus, I'm asking, would this be considered acidic or basic? And what do we learn at 25 degrees Celsius, Kw is equal to? Yep, exactly. So if you see 25 degrees Celsius on one of these problems, that's kind of like a giveaway to me. Like we can use Kw as 1 times 10 to the minus 14. Um, and as a rule of thumb, I think Blumling pretty much always makes it 25 degrees Celsius. So you can kind of use that Kw conversion. So spend a few minutes working on this one, see if you can find that hydroxide ion concentration, and then using that, see if you can figure out, would we call this more acidic or more basic? All right, let's go over this one. Also, I want to give a quick review of what Kw is, because I know in the past couple of weeks we've probably heard of 5 new K values, give or take. So it can kind of get confusing. Don't overthink it. If you see a capital K, most of the time it's going to be another version of one of these ionization constants. Yeah.
Why would you do the thing where you like, you like the negative log of it and then you minus 1014 to get it to pH and pOH and then back to OH?
That's a great question. So I'll get into that because there are, with a lot of these problems, you're going to learn there's a few different ways we can do it. So give me 1 second, I'll get back to that. And we have a few more practice problems like this. So I'll kind of show when to do that step and when not to.
But I
Mhm. Okay. I'll come take a look at your work in a second as well. But first, real quick, again, Kw is a way of representing the ionization of water. So this is something that is easy to kind of like overlook after you work with Kw so many times. But again, we're dealing with a liquid going to form 2 different aqueous ions. Remember, since day one of learning about these capital Ks, liquids don't go into K constant. So that's why we write Kw as the concentration of OH minus times the concentration of H3O plus. These are simply 2 aqueous ions. They're in the product. Remember, it's product of a reactant. So you can kind of think of this as over 1 because we don't have any reactant because it's a liquid. So we don't put it in the K constant. But now we got to get to the math part. So we found, we were told the concentration of H3O plus as 6.2 times 10 to the minus 4. So we can plug that in right here as the concentration of the hydronium ion, and then do a little bit of algebra to do Kw, divide this on both sides. So Kw divided by the H3O plus gets us the OH minus concentration. And the reason why we don't go a step further is because all I asked for in this question is straight up the concentration of OH minus. If I were to ask you what is the pOH or what is the pH, the next step would be then to take the minus log or the inverse log of this concentration, and that would take us to pOH. So we can find out if it's acidic or basic without even finding the pH, because what do we have here? We have a value for the concentration of H3O plus and a value for the concentration of OH minus. H3O plus is 6.2 times 10 to the minus 4, and OH minus is 1.61 times 10 to the minus 11. So this is way smaller than this one, right? So we could say that we have a lot more hydronium ion, meaning this is going to be acidic. Let me come take a look real quick.
So, if it's a negative volatile, and then we have this, and then that will go and get the heat, maybe, yeah, like, that's what's in the like that, and then with the inverse law, so it's find out negative and times into
So that should actually work. Yeah, so what you did there is you went from having the concentration of hydronium ion straight to the pH, putting the negative log of that. And then once we have pH to the right, we can 14 minuses to get pOH. And then if we want to get that concentration of hydroxide, it's 10 to the minus of that, 10 to the power of minus that pOH.
Okay,
So maybe in your calculator, it could simply be like a scientific multiplication goal, but that is another way we can solve it.
maybe we can. And this 7. Well, either way, I feel like this makes something. That's now, because it has negative 11, and it's probably just a rounding thing, but, so can I just think of it as like, if it's H to OH, you can just do it this way, and if it's pH to pOH, that's gonna be just minus it completely, but if it's like H to pOH, then I would just.
Yeah, so if you ever need to get pH for pOH as your answer, that's when you're going to be doing steps of taking the inverse log. On this problem, I'm kind of giving it as a starter one. We can straight up use the Kw and do Kw divided by H3O plus to get OH minus. But I think one of the next ones we will have to do some of the work like what you did there. Skip this because I already wrote it up for you guys. I was asking what is the balanced chemical equation for the ionization of water? We did that here. I just want to make sure you guys have a good understanding of what Kw is, why we can use it for these things. And since it is a constant, and again, what's the only thing that can alter the equilibrium constant? Temperature. Yep, that's why it matters so much that he always explains at 25 degrees Celsius, because that's how we can know we are using the 1 times 10 to the minus 14 as Kw. This is a good one though. What is H3O plus and OH minus when pure liquid water is in equilibrium with hydronium and hydroxide ions at 25 degrees Celsius? This is a fancy way of asking at equilibrium when we have this value, we can calculate the concentrations of both hydroxide and hydronium. And pure liquid water, I should probably say neutral pure liquid water because I'm trying to stress that we're at pH of 7. And the answer for this one is at pH 7, we have equal concentrations of both hydronium and hydroxide. So they're both going to be, if it's this times this equals that, they both need to be 1 times 10 to the minus 7. Does that make sense? I don't need to go in depth on that one. Okay, gotcha. Yeah, so you have a solution with hydronium ion concentration of 0.0025 molarity. I'm asking you to calculate the pOH. So this one we do need to do a couple steps. Hopefully this will focus. So spend a few minutes working on this one. Can you guys see that okay? I know it's written in a weird font. This was honestly my favorite unit when I took this class by far. I thought it was kind of cool how with all these problems, you have a few different ways, whatever way is most comfortable for you. You can take a few extra steps, you can take a few shortcuts, but you're going to get the same answer as long as you do it right. Anyone get an answer for this one? Mhm. Yep. And you're always going to report pH and pOH values to the hundredth, so the second decimal. So 11.40 technically. But here's how I solve it. I'm curious if anyone solved it a different way. But I think the quickest way to do this one is we have a hydronium ion concentration given to us. And anytime we have a concentration of either hydronium ions or hydroxide ions, we can go straight to the either pH or pOH, respectively, um, by doing the inverse log of that. So pH is inverse log of that concentration. That gets us 2.60. By the way, we're talking acidic or basic once we see this value. Acidic. Yep, this is pretty acidic. And we could figure that out right off the bat. They told us the hydronium ion concentration was 0.0025. That's not that small, relatively. We're seeing some numbers that are like times 10 to the minus 11, times 10 to the minus 12. So this one's really only times 10 to the minus 3, I guess, if we wrote it that way. So right off the bat, we're like, all right, pretty acidic. So I should expect my pH to be low and my pOH to be high. So again, there's a lot of times you can kind of pause, take a checkpoint, be like, does this value even make sense? And then again, of course, the last step, the easiest one, going from pH to pOH is 14 minus the pH. So 11.4. And still to this day, if you asked me, what does a pOH of 11.4 mean? My brain doesn't really work that way. I could probably, after 20 seconds, be like, that's probably acidic. I don't ever think about things in terms of pOH. I always think of pH because the pH scale has been kind of ingrained in my head since like middle school at this point. I know a low pH is acidic, so I always revert back to pH and figure out, all right, is this acidic, basic? And then we know pOH is going to be the opposite. So, um, right, if somebody gave me a pOH, I would just do 14 minus it to find the pH and then go from there when we're talking about, is this acidic or is this basic? But you do what works best for you. All right, we have a couple more. Um, let's see. A neutral solution of water at a particular temperature. So key point here, at a particular temperature, meaning we don't necessarily know if Kw is going to be 1 times 10 to the minus 14, has a concentration of hydroxide ions equal to 4.3 times 10 to the minus 7. Calculate what Kw is at this temperature. So A few keywords. This is a weird problem. It's possible he would give something like this on your test. I do remember when I made this a few years back, this was an active problem, so maybe your active homework had one like this. There's one extremely key word here. Does anyone want to guess? Not concentration, although that is important. Neutral. Yep. This word right here, highlighted 1,000 times. This is the only way we can solve this problem. Because what does something tell us when we call a solution neutral? pH of 7. Yep. And so we now have a starting point that we can work with. But let's go back a couple questions ago. We said that at neutral pH, hydronium ion concentration is equal to hydroxide ion concentration. So I'm not going to give you any more hints before you guys go solve this one, but that's a really key point is that at any time we're at pH 7, the amount of hydroxide is equal to the amount of hydronium. I remember this question really confused everyone, including the class that he put it up. So don't worry if you're feeling a little confused. We'll walk through the thing. Yes. So again, really important detail here. We said that at pH 7, the amount of hydroxide ion is equal to the amount of hydronium ion. So again, let's go back to what Kw is. Kw is OH minus times H3O plus. And we have one of those values, and we know that the other one's the same. So we can basically say that Kw is equal to OH minus squared, right? They're the same thing. So the answer here is really just 4.3 times 10 to the minus 7 squared. We can plug that into our calculator. And we find that it's close to 1 times 10 to the minus 14. Not exactly the same, though. It's 1.85 times 10 to the minus 13.
So what is the 7?
The 7 right here, that comes back to, again, the way we defined the solution of water was neutral. Anytime you see the word neutral, we're at pH 7. It's neither acidic or basic. It's right in the middle. So yeah, exactly. So I use that kind of as a starting point. We need to know that when we're at neutral pH, there's some rule that we can use to finish this problem. Um, and the way that you need to do this one is always remember at pH 7, we have equal concentrations of hydroxide ion and hydronium ion. You couldn't solve this one with this little amount of information if it wasn't at neutral. Yeah, that was kind of the key thing on this one. Exactly. Yeah. And this is like the only instance you would do that. This is a very weird kind of specific problem, but um, it was in a homework one time, so it's not impossible. You see it. Everyone feel good about that one? All right, last one for this stuff, and then I threw in a Le Chatelier's review problem because um, I was sick on this past weekend, so we didn't get to do a full in-person session on this. But this is kind of a really good run through again of all these rules that we learned. So Spend a few minutes. Once you find one answer to this, the other answers start kind of flowing in afterwards. So we have at 25 degrees Celsius, so Kw is 1 times 10 to the minus 14, a solution that's prepared by dividing 0.0250 moles of sodium hydroxide in enough water to make 500 milliliters of solution. By the way, what is sodium hydroxide? It's a base, strong base. Yep, it's one of those strong bases that you got to memorize. So I gave you the amount of moles and the total volume. So that should be kind of an indicator that we can end up finding a molarity value. So spend a few minutes working on this. Even if you only get one of them, if you get none of them, no worries, we'll go through it. But start with trying to find the hydroxide ion concentration first. And it's important to remember that strong acids and strong bases fully dissociate. So if you're kind of at a stuck point right here, anytime we have a strong acid or a strong base, we know that 1-to-1, it's going to dissolve fully into those hydroxide ions. So when you write NaOH, this is a key detail that's going to come up. It's not even at equilibrium. It's going to be a forward arrow, and that's it. Fully breaking off into Na plus ions and, look at that, hydroxide ions. And I'm pretty sure he'll talk a lot about this tomorrow and in the coming classes. So yes, exactly. That's the key detail here. So once you find the molarity of sodium hydroxide, that's the same as finding the molarity or the concentration of hydroxide ion. So we can go ahead and do that real quick. That first one shouldn't be too bad. 0.025 divided by 0.5, because it's moles over liters, is 5 times 10 to the minus 2, or 0.05 molarity is that concentration of NaOH, which again is equal to the concentration of OH minus. So we got the first one. And now we can do a lot. There's a lot of things we could do here. A lot of ways we could go about solving the next few. So yeah, spend a few seconds working on the next one. Someone tell me, if we have the concentration of OH minus, what's probably the fastest way that we could get pOH? Inverse log. Yep. And again, these steps, if they're not like, if you have to still look at your notes, it's totally okay. It takes a little bit of time to memorize all these. But again, anytime we're going from concentration of hydroxide ions, the negative log of that is going to get us our pOH.
We don't have them.
No, that will be though for the very next one. So in fact, it's very important that you don't yet. So anytime you're dealing with OH minus, we can't go straight from the concentration of that to pH. We would have to go to pOH and then do 14 minus to get pH. Also, everyone doing okay with calculator stuff? I had a lot of people in class the other day ask me for help with their calculator. So the pOH is 1.30. Again, I see that number as a pOH and doesn't really click in my brain. I need to do the next step, which is that pH is 14 minus that, which is going to be 12.70.
Let's see.
That's C. Yep. So let me go through and label these: A, B, C. This one, please. So to do question D, there again is a few ways we could do this. I think the best way to do it is the way of going from pH to hydronium ion concentration, which is 10 to the power of minus pH equals H3O plus. So that's 10 to the power of minus 12.70. They're really having a good time over there. I don't know. I feel like I'm missing out. And this value is approximately 2.00 times 10 to the minus 13. And now if I asked you if this solution is, that looks like a 1. It's supposed to be a 2. If I asked you, is this acidic or basic? We have so many different ways we can answer this now. The easiest one is we're starting with NaOH. That's the immediate giveaway, strong base. It's going to be basic. But my way that I would probably answer that if I didn't have that clue in is pH, because that's the simplest. Again, the pH scale makes sense in my head. I know if it's a really high number, like 12.7, really basic.
But then when you find H constant, if the 2.00 times 100, that means it's really acidic, right?
Opposite. So 2 times 10 to the minus 13 is a really, really small number, whereas 0.05 is OH minus.
Both sevens.
That's right. Yes. So don't get the concentrations confused with the pH scale. pH is only able to be from 1 to 14. That's it. Once you start getting to the times 10 to the minus and stuff, you're talking about concentration values. And this value of times 10 to the minus 13 is really, really small. So that would tell me that we don't have a lot of the hydronium ions, meaning we have to have a lot of the hydroxides. So this is going to be basic. And then is everyone okay with that? This is a 2 right here. Yeah, sorry, it's a horrible 2. And then I said bonus, verify this using KW. And a way we can do that is since we have the OH minus concentration and the hydroxide ion and the hydronium ion concentration, we know that KW should be 1 times 10 to the minus 14, but let's make sure. So this is equal to 2 times 10 to the minus 13 times 0.05. Plug that into our calculator. And look at that. Lo and behold, it's 1 times 10 to the minus 14. Kind of a good way of making sure all of our work is good. All right, Le Chatelier's principle. I wanted to toss in this so we can make some talk about it in case you guys are confused about this part. We have a reaction here. This is a pretty fundamental chemical reaction called like the Haber process. I don't know anything beyond that, but I see this come up every time there's an example of Le Chatelier's or something else. So we have 2N2 plus 3H2 going to form 2NH3. Key detail here is that we are at equilibrium by those equilibrium arrows. And then also some other things that I would immediately look at when I see one of these types of problems is all things in this problem are in the gas phase. That sometimes comes up to matter. I think I talked about that in one of these problems. And the delta H is minus 3.02. So is that endothermic or exothermic? Exothermic, yeah. So would I write that as a reactant or a product? As a product, yes, exactly. I always do this right off the bat so I don't confuse myself. If something's exothermic, that means we're basically releasing it as another product. So I'm going to put over here 3.02 kilojoules per mole in the products. It helps me think about this stuff. So let's see what they're asking us. First part, what would the addition of heat do to the position of equilibrium? Shift to the left. Yep, exactly. So addition of heat, well, where's heat in this problem? We added it as a product. If we were to increase a product, Le Chatelier's principle says that we're going to start going to form more of the left side because we're basically adding a product. We don't like that. If we start forming more reactants, we're going to get back to equilibrium. Next part. If the container this reaction took place in went from 10 liters to 2 liters, how would the position of equilibrium respond? So first off, going from 10 liters to 2 liters, what's happening to pressure? Increasing. Yep. And so when pressure increases, we go to the side of fewer moles of gas. So do we think we're going to shift to the left or shift to the right? To the right, exactly. We have 2 moles of gas on the product side and 2 plus 3, 5 moles of gas on the reactant side. So if we increased pressure by lowering volume, we would shift to the right. So A, B, and then C, last one. I gave you the easiest one as the last one. If the concentration of H2 were increased, how would equilibrium respond? Right, exactly. Anytime you add a reactant, we're going to shift to the product side. Cool. You guys feel pretty good with Le Chatelier's principle? Nice. Yeah. This is like with Le Chatelier's, yeah, that one's probably the hardest rule to remember. And again, it can sometimes he might trick you where he'll throw in a liquid or a solid into the equilibrium reaction. Remember that doesn't factor in. We're only talking about moles of gas when we're dealing with pressure shifts. Yeah. But other than that, Le Chatelier's should hopefully be a couple free points on your test. Not too bad of a principle. And it comes back up a lot in biochem and other classes.